Alrighty. So the last couple of topics that we're going to cover, it's going to be the Doppler effect, all right, and a little bit of interference of waves, all right. And then if we can get these two sort of finished, then I think that's complete the material that we're going to cover in the midterm exam. So that should be good. Okay, so let's start with the easy one. So we're going to start from the Doppler effect, which is the effect due to the movement of the source or the observer relative to the wave itself, right? So you sort of understand that every time that the wave hit, because we are focusing on sounds wave right now. So every time that you have the sound hitting your ears, you receive the sound's frequency at some value. But of course, the value of the frequency will change depends on how many hits you receive in your ears per unit time, because the frequency is just the number of cycles of the wave that hits you per second in the unit of hertz, of course. So that means if the number of hits increases, so you will interpret that is a higher pitch sound. So it means the frequency of the sound will be higher. If the number of hits that go to your ears is lower per unit time, so you're gonna hear a lower tone sound. So you're gonna hear a lower frequency sound, all right? So now you can see that the number of hits that can get to your ears can change due to two things. It's either the source may be moving, or maybe you are actually moving relative to the sound itself, okay? And the change of the frequency due to the movements, we call it the Doppler effect. That's the key thing, okay? So what we are looking at right now, it will be three things that we will be able to, three velocity that we're going to have to discuss. Of course, first, velocity or the speed that it has to be there all the time is the speed of sound. Of course, we cannot escape that. And because right now we have two parties that we are looking at, so it's either an observer. So observer, we're going to use O for that. And for the source, we're going to use S. And because we are allowing these two to move, so they will have their own velocity. So we can use a subscript O, V of observer. So it's a V sub O representing the velocity of the observer, and V sub S representing the velocity of the source. Okay, sounds good? And of course, because the source is a source of the sound, so that means the sound that generated by the source will have the original frequency. All right, so that we're gonna use subscript S for that. So F sub S will represent the frequency of the source. Okay, and of course, the main goal of the Doppler effect calculation is to calculate the observed frequency, and that will be the F sub O. All right, and that's pretty much it. So in the sense that we are going to focus on the frequency first, and if you really want to get back to the wavelength, you can do that through V equal to F lambda all the time. So that's no big deal. So if you want to figure out what is the wavelength that the observer can observe, then you can just use the subscript O for that. So that's an easy one to go. Okay, so when you receive a shifted frequency, F sub O, that's a new frequency due to Doppler effect, then you match it with the velocity of sound, then you can calculate the shifted wavelength along with it as well. But anyway, I think the main focus will be on the frequency, because that's the one that we sort of try to look at. Okay, now, how can we calculate the observed frequency due to the motions of source and observers? And that's the whole thing of this topics right here. And now, when you look at the slide, it's like, okay, what's going on? Ajahn is like coming back and forth, going forward, backward, relative velocity, blah, blah, blah. Don't worry about it. Okay, so this slide is just for those who seek some adventure. All right, but for the main audience, the majority of us, we would love to see what is the final effect of this one. So There are two sides of the story, of course. So this slide is talking about when observer is actually moved. Oh, sorry, is at the source. Okay, when the observer moving toward the source. Okay, what will happen? And then what happened when the observer move away from the source? What's happening? Okay, and of course, when the source is in motion, so this slide is for what is going on when the source is moving toward the observer. And you can guess the next slide will be what's going on when the source moving away from the observer. Okay, sounds good? All right, but anyway, all in all, because we don't want to go back too far in terms of proving the formula or verifying some formula. So I think the way that we want to do is this. And I think this is the one, this is the take-home message here about the Doppler effect is right here. Okay, so what you can see right here is I am representing this formula in terms of first, this is the original frequency from the source, F sub S. Okay, sounds good. And I put the observed frequency on the left. That would be sort of the final observed frequency that you would like, or that you would hear. Okay, and of course, those three velocities or the speeds that come into play is already in here. So there's a V, okay, that's the speed of sound, and V sub O, V sub S right there. And I put them all in the bracket over here. So you can see from this formula, whatever you're gonna get out here, you only going to get a number because the numerator is velocity, the denominator is velocity. So this is a dimensionless quantity. So this is just number, okay? So this is good. So if the number is 1, what does it mean? It means whatever the frequency of the source is, that is the frequency that you're going to observe. It sounds reasonable. All right, let's make it a little bit easy. So if this one go greater than 1, so that means the observed frequency will be shifted up in frequency. Or if this ratio over here is less than 1, so it means the observed frequency will be lower in frequency. So you will hear a lower tone. And that's it. That's it in the sense that this is the structure that I'm giving it to you just for sort of calculating the Doppler effect. Now, the task that's left for us is what are these signs that we're supposed to pick for the scenario that you are facing in Doppler calculation? Sounds reasonable? And when I say, what are the scenarios? Do you think how many scenarios that you can get out of this? There is a source, there is the observer. So in all combinations, you're only gonna get 4 combinations. It's either the source and observer moving toward each other, that's 1. Moving away from each other, that's 2. Moving along the side of the observer, that's 1 way. Or moving along the direction of the source. That's it. So there are only 4 combinations that you can look at. So what else can we do? That's it. All right. And the easier case is when one of the two, either observer is stationary or maybe the source is stationary. And if that is the case, it's even easier because the velocity is 0. So that would be the easier case. All right. So that's what we are trying to get to. All right, here we go. Oh, I think I forgot to add some additional space right here. So I'm going to add a page. Okay, give me 1 second here, guys. Sorry. Let me edit pages. I'm gonna add one here. Okay, let's do a landscape mode. All right, so let's go from this. All right. So you guys hearing me okay, right? So, okay, seems okay. Just check for the response a little bit. Okay. Cool. I hope I'm not talking to myself right now, right? I hope. Okay. Maybe just type 1 or something. Just notify me a bit. Oh, thank you. All right, here we go. Okay, so we might have the observer on the left, and there is a source on the right. Yep. Okay. And then in the case that observer is actually moving to the left and observer moving to the left and source moving, well, I'm confused. Observer moving to the right and the source moving to the left. So in this case, they are sort of approaching each other. Okay, so my plan is this. This is my structure. This is what is always going to be sort of set. Here we go. All right, this is a structure. And then the rest is picking up the correct sign to use. First of all, the logic is very simple. You think what will happen when the observer is approaching the source? Do you think the observed frequency will be higher or lower? Yeah, of course, it's supposed to be higher because you are approaching the source, right? And when you look at the formula over here, the observer velocity is in the numerator. So you want the final effect to be the increase in frequency. So I pick positive sign on top. Sounds good? Okay, one more. Try again. What about the source? When the source is approaching the observer, do you think the observer will hear higher frequency or lower? Of course, it will be higher, right? Because that's what you sort of observe when like motorcycle pass you by, like super fast, like nyum, nyum. So when it's approaching you, the frequency is up, and when it's sort of like going away from you, the frequency drops. So that's why it's saying, so it's coming in as a, and then going out is a, So when the source is approaching you, the frequency will be higher. However, because the velocity of the source is in the numerator, in the denominator, you want the final effects to be a bigger frequency. So you want to make the denominator smaller. So you pick negative sign in the bottom. Sounds cool? You get the logic that what I'm trying to get to. Okay, all right, try again, one more time. Let's do what's going on when the observer and the source are separating. So now they're moving away from each other. So once again, I'm gonna set up the structure of the Doppler equation, just like that. Okay, looks good, yeah? All right, let's start from the observer. Observer is running away from the source. So the observed frequency should be lower. However, because the observer velocity is in the numerator, right? So I pick negative sign there. Lower the net number, all right, V minus something. Okay, now look at the source. The source now moving away. Frequency should be lower as well. But because the velocity of the source is down here, you want the final F sub O to be smaller. So you pick the positive sign there. Sounds all right, reasonable. Okay, try again. We have 4 cases, of course. Let's finish those. So you will have the case when the observer moving toward the source, but the source is running away. So what do you think it will happen? Okay, so let me write out the main structure of the equation. It will look just like this all the time. Okay, now observer moving toward the source. Frequency should be higher, so you pick positive. And the source running away, the frequency should be lower, but because the vis-a-vis is underneath right here, so you want the negative sign. I'm sorry, the positive sign. There you go. Okay, sounds good. Okay, last one. So let me finish the diagram here. So you see all 4 cases all together. So now the observer running away from the source, but the source is running toward the observer. And that's fine. Okay, let me write out, oops. Once again, the structure of this equation will look like this. Cool. All right. Observer running away. Frequency should be smaller. To make things smaller, you pick negative sign for the numerator. Now for the source is approaching the observer. Frequency should be higher. But because we are talking about the denominator, to make the final numbers bigger, you want the denominator to be smaller. So you pick negative sign at the bottom. That's it. Complete 4 cases. Okay, so actually, if you want to categorize for, so of course, for individual observer or the source, the observer have 2 choices. Is either approaching or running away from the source. Approaching, you pick the positive sign. Running away, you pick the negative sign. That's for the observer. Now looking at the source side, the source going toward the observer, then you pick the negative sign. That's in the bottom. Okay. And when the source running away from the observer, you pick the positive side. That's in the bottom. That's it. With this 4 choices, I mean, you just pick one of the 4, and then you should be able to calculate pretty much, well, Doppler effect for one-dimensional movement like this of any kind. It works all the time. Sounds cool? All right, let's practice. Okay, so we're gonna put this to test and see how it goes. Okay, any questions? I think it's kind of like good conclusion because we skipped like a couple of slides proving these formulas, right? All right, here we go. All right, let's start up using those sort of combinations for this problem here. A train is moving parallel to a highway with a constant speed of 20 meters per second. Okay, so let me sort of draw a diagram of it. So you have a train running, all right, 20 meters per second, that's fine. 20 meters per second, very good. Now there is a car is traveling in the same direction as the train and actually faster. Okay, good. So there is a train and there's a car. This one has a larger speed. Well, I should draw a longer arrows, but that's okay. Okay, now the car horn sounds at the frequency of 510 hertz. So they just like horn the sound 510 hertz. And the train whistle sounds at 320. That's 320 hertz. There you go. Now, let's try part A. When the car is behind the train, okay, that's in the scenario that we're having right now. What frequency does an occupants of the car observe for the train whistle? Okay, so the key point of this one is, of course, you have to be specific who is going to be observer, who is going to be the source, because right now they're both generating sounds. Okay, so for part A, of course, they're talking about the occupant of the car that's observing the sound. So this means the observer is right here. And the source that we are talking about is the whistle sound. So the source is with the train. Sounds good? Cool. Now, let's do the calculation here. So what we want to calculate the observed frequency. Now I set up the structure of the equation just like before. There you go. And now here we go. Start from the observer approaching the source. Positive and negative sign, guys? Of course, positive. Okay. And what happened for the source? The source is running away. Okay, running away, it means lower in frequency. But then because everything is in the denominator here, so you pick a positive sign right there. That's it. So if you look at this one, is the case that observer is approaching the source running away. So it's gonna go like this one. All right, but you can use the logic of, you know, what's going on with the final observed frequency to pick the correct sign in this case. And now, once you know what the sign you should use, then just plug in the number. Usually in the exam, they will give you the speed of sound. So that shouldn't be a problem. We can use like maybe 145 or maybe, I'm sorry, 345 or 340. That would be a given amount in the exam. Now, the velocity of our observer is going to be the velocity of the car. So it's going to be 40 divided by speed of sound, 345, plus the speed of the source. The source is the train speed. So 20 is down here. And the sounds that we are hearing right now from the source is from the whistle sound. So it's 320 hertz. And that's it, done. Okay, and I think by showing you this exercise, it's nice to notice something here. Look at this one. When we are considering the direction of the observer or the source, we don't care what's going on to the other party. So for example, when I say, hey, the observer approaching the source, I don't have to worry about the source is going away or going towards me. I don't care. I just looking at what is going on with the observer, and the observer is sort of like, okay, go toward the source, and then I'm good. Okay. And the nice thing about that one, the reason we don't have to worry about it, because look at this number. Okay, I can add this number a bit. See, the good thing about this number, I mean, this calculation over here is when you look into this ratio right here, the ratio is greater than 1. What does it mean? It means the occupant of the car will hear the higher frequency sound due to the movement of the car relative to the train. And that makes sense because the car is actually going faster than the train. So overall, to the occupants of the car, actually the car is approaching, right? Because catching up to the train. So in effect, it will look just like the car is actually getting closer to the train. So of course, the net frequency that they will hear is going to be a higher frequency. But as you can see, these numbers is already there. The ratio is automatically greater than 1. Okay, you see what I'm saying, right? So you don't have to worry about the directions of the other party, because eventually the magnitude of the speed will take care of the final result. That's what will happen to the net observed frequency. Sounds cool? All right, try again. So if this seems to work, then I think that's sort of, you understand how things goes, then the calculation of the Doppler effects will be quite straightforward. Try again. Now part B, after the car passes and is in front of the train. Okay, very good. So now let me sort of, let's say it's already overtake the train. But of course the speed stays the same, 40 meters per second for the car. Okay, there's still horn sound, same frequency, 510 hertz. Now, part B, they say, what frequency does a train passenger observe for the car horn? So now the thing is, you have to make sure that you sort of have to switch the role, because at this point, the part B questions now asking what will happen to the passenger on the train now. So that means for part B, the observer is now a passenger on a train. So let me put O here, but let me put prime in here just to distinguish part A and part B. Okay, so O prime, that will be your observer for the part B. And now the source is going to be the horn sound. So let me put S prime there. So that means for the part B, now the source is now going to be the 510 hertz from the car. And now we are looking at what will be the frequency observed by the passenger on the train here. Let's do it. So F observed, so let me put prime in there. So F sub O prime, set up the structure. Okay, and then just put prime in everywhere. Okay, but just distinguish part A and part B, that's all. Okay, and now what should be the sign, guys? Woohoo! Now, in this case, observer approaching the source and the source running away. So actually, it's exactly the same as the first case, right? Okay, that's fine. So observer running toward the source, you pick the positive sign on top. The source running away from the observer, you pick the positive sign in the bottom. Okay, cool. And now at the end, you just substitute the value. And now don't forget the who's, right? In this case, the velocity of the observer is going to be the velocity of the train. Okay, and the velocity of the source in this case is going to be the velocity of the car. So that would be 40. Here we go. All right, and the source frequency is going to be the horn sound from the car. So we have to multiply by 510 hertz. And that's it, that's done. And you can notice once again, the mathematics takes care of everything. The ratio that you have over here is less than 1. Which is the case because, I mean, from the perspective of the people on the train, the cars actually running away from them. So you're gonna hear a lower frequency sound. Okay. Oh, what was the question, guys? Oh, thank you. Yes, correct. Very good. Plus. That's correct.
I have a question.
But that's character. I don't know. I haven't called that for a long time. นั่นมันตัวหนังสืออะไรวะ
อาจารย์ I have a
ไม่ใช่
question
รอ
ครับ
ไม่ใช่
Hello
สอฤาษีรอศาลา
Hello อาจารย์
ไม่ได้ละ What is this one? Okay, anyway. Cool. All right, it's been a long time. I haven't used that. Okay, all right, but that's pretty much what is it for the Doppler effect. Okay. And let's do one more, just to do a quick practice. Oh, yes. Go ahead. What's the question?
Ajahn, can you hear me?
Yeah, you can speak right away. Yeah.
So what if actually the formula is that O is at the left and then S is at the right?
For the formula, yes.
Yeah. How about what if S is at the left and then O is at the right? What happens?
Oh, you have to switch the ratio as well if you want. Yeah, you can flip that over as well if you want.
Oh, okay. So
Yeah,
the formula doesn't change.
Everything will go just like before, but seems to be like I would like to focus on the observed frequency, so that's why I put the F sub O on the left.
Okay,ครับ.
So it seems like, yeah, F sub O will be sort of like the final numbers that you would like to calculate. And then I throw everything, all the informations given on the right.
So just focus on the observer is like going away from the source or like following the source. Just
Correct.
focus on that, right?
Actually, for both of them. Right? Because you always have to figure out the direction of both observer and the source. Okay, but the observer, you will be focusing on the numerator part. And for the source, you are focusing on the denominator part. Okay, you have 4 cases over here. Sounds good? Yeah? Okay. Okay, you kind of like disappearing on me.
Yeah, I understand. Thank you.
Okay, all right.
I got it.
All right, so let's do one more. Well, that will be fun, but that's a good question because actually it's sort of like a flavor of the way that you write out the equation. But this is the form that I think people prefer the most, I would guess. I would sort of like most of the equations in the textbook goes for this format. So that's why it seems to be a standard approach to this Doppler effect calculation. Okay. All right, cool. Okay, next, try this one. I think this is going to be I would say the hardest one for the Doppler effect calculation. So for our exam, it's not going to go beyond this for sure. And I think in the exam, we'll go just to check that you know how to apply the Doppler effect equation properly. That's it. All right. But just to show you what's the sort of like the coolness, that's the coolness. It's like the benefit or the advantage of knowing the Doppler effect and then what kind of application it will be. This is a good example to showcase that. Okay, so let's take a look at this. So you have a bat moving at 5 meters per second and chasing a flying insect. All right. Now, if the bat emits 40 kilohertz chirp, all right, so that's good. So let me sort of draw a bat right here. There you go. And generate some super high pitch sound. Of course, that's not audible by human because we have the upper limit of hearing of about 20 kilohertz, somewhere around there. But this one is going to be ultrasonic. Okay. Now, the bat itself receives an echo, which has higher frequency. And because the bat is chasing an insect right there, of course, that echo is the reflection from the insect back to the bat. Now, at what speed is the insect moving toward or away from the bat? Take the speed of sound to be 340. All right, so that's given. Okay, so let me write the speed of the bat to be 5 meters per second. Okay, how would you approach this, guys? What do you think? This is kind of weird a bit in the sense that the bat acts like a source and also an observer, right? And that probably not going to be able to get things done in one step because we cannot have a single object to be both source and observer at the same time. So that's a clue telling us that we should split this calculation into two halves. The first half is when the sound travels from the bat to the insects. Sounds good? And then there will be an echo. So that's coming from the reflection. So on the way back, the insect behave like a source and the bat will behave like an observer for the second half. Sounds good? Okay, so for the first half, the bat will be the source. So let me put here. So let me put down here, yeah? So the source, that would be the first half. And insect will be observer. Let's do this one first. However, at this point, we don't know what is the speed of the insects. So let's give it some speed and direction because we don't know. So I'm going to assume that the insect is approaching the bat because the frequency is higher, maybe. All right. However, once again, the mathematics will take care of the rest at the end. Okay, so let's start from the first leg, the first half. The bat is the source and the insect is our observer. So I'm going to set up if that's going to get observed, going to be equal to the ratio, okay, between those speeds times the frequency of the source. Okay, guys, what should be the sign in this case? Observer moving towards the source, moving towards. Very cool. It's going to be positive and negative. Very nice. Okay, and then let's substitute the number a bit so you guys see what's going on here. So of course, the speed of sound is 340 plus the speed of the observer, which is x, we don't know at this point, divided by 340 minus speed of the bat, 5 meters per second. Cool. And multiply by the source frequency, which is in this case that 40 kilohertz. Let's just put it there. That's it. There's nowhere else to go because we still don't know what the x is supposed to be. So let's try the second half. Now for the second half, the source is from the reflection, but I'm going to use the prime just to distinguish the first and the second half. Yeah, just like before. And now the bat is going to be the observer. So I'm going to put the O prime in here. All right. And what you get over here is, once again, let's set up the equation. There you go. The same structure. But then I'm going to put prime in all of these because we're talking about the second half. Okay. So what should be the sign, guys? Now the source is, of course, it's going to be the same because the source is approaching, the observer is also approaching toward each other. So it's going to be positive, negative again. Very good. Positive, negative. You guys with me? Okay. But, of course, I'm going to have to substitute numbers here just to clarify things. In this case, the velocity of the observer in the second half is now the speed of the bat. So it's going to be +5 here. And the speed of the source for the second half is going to be the speed of the insect, which is x. Cool. All right, even though the signs are the same for two halves, but the velocity that you put in there is going to be swapped because the row are switched, swapped as well. And now, here's the key. What should be the frequency of the source in the second half? Of course, it's just the reflection. So that means whatever the insect here in the first half, that will get reflected back right away. You guys with me? So that means the source frequency for the second half come directly from the observed frequency from the first half. That's right there. Just relate it. Cool. So that means I'm just going to take the whole chunk, plug it in here. So that will be 340 plus x over 340 minus 5, 40 kilohertz. And what should be the numbers on the left-hand side? Of course, that will be the observed frequency after the echo. So that would be 40.4 kilohertz on the left. And I'm, well, not done, but almost done. Because you can figure out what should be the x meter per second. Yeah? All right. And when I say the mathematics will take care of everything, because even though you assume in the first place that the insect's velocity is toward the bat, that means if the final number is positive something, then that means your assumption is already correct. So the insect actually really approaching the bat. On the other hand, if you come up with the negative number, okay, that's not a zero, it's number. Or if you solve this equation and you get a negative value for the x, that's okay. It just means that the insect is flying away from the bats. See, so that's good. The sign will take care of the direction of the velocity of the insect automatically. Cool. I keep saying cool. The reason I say keep saying cool because this is an example that showcases the sort of like the characteristic of the Doppler effect. Look at this. You can actually calculate the speed of the insect by just checking the shifted frequency from the echo. You see what this is going? So this is what exactly you can do when police shining like a speeding gun, sort of, to check the speed of the traveling car. they actually use the Doppler effects as well. So when they shoot one frequency toward the car, if the car is moving, the reflection frequency will shift it. Okay. And then from that shifted value, you can sort of, calculate back what should be the speed of the car. Mm, yeah. Another example is when we know that the galaxies in our universe is actually sort of like running away from each other, is expanding, universe is expanding. That is because when you try to observe the frequency from, for example, maybe the light generating by some other stars, for example, then if you know exactly that actually maybe that's supposed to be the spectrum of hydrogen gas, and we know exactly what hydrogen gas should just give out what frequency of light, but then the light that reaching Earth has the shifted frequency, and it turns out the frequency is actually lower than it's supposed to be. So you know the source must be running away from us. That is also Doppler effect, and that's good. That's confirmed that, oh, the source is running away from us. And when you look around it, everything is running away from each other. So you can sort of conclude that the universe is expanding, something like that. So you can also use this to detect, for example, the blood speed in your vein or in your blood vessel by doing the ultrasound. You sort of like shoot the ultrasonic sound inside your bloodstream, and then you listen for the reflection from it. Then you can calculate how fast your blood flow is going, something like this. So every time that you try to detect the speed of something, you can do it through Doppler effect by shooting at it with some frequency and detect for the change in the frequency on the way back. All right, I think that's a cool technique. We use it so much, actually. All right, nice. Okay, so I think this is definitely, I think, worth it because this will show up in the midterm for sure. And I'll have already shown you how easy it is to calculate by starting from the structure of the equations. So the only mistakes that might happen is just you pick the wrong sign, I think. Or maybe you substitute the wrong velocity. So that would be a shame. Okay, all right. So that's done for the topic of Doppler effect. Sounds good? Okay, here comes the last topic that we're going to do. And it's quite okay because it's still algebra. Yeah, we don't have any calculus involved here anymore. So that's kind of nice. So the last property of waves that we're going to study is something we call interference. Okay, so I mean, we use the word interference all the time, and it's, well, it's in kind of in a bad way because, like, you know, Wi-Fi get interfere, something like that, when you have so many people using Wi-Fi at the same time, and then your Wi-Fi signals get interferes and all this. But this is not what we are, well, that's the source of that word. This one, we are looking at the interference of waves. So waves can interfere with themselves. And the way that it goes is very simple because that interference is based on very simple principle. We call it the superposition principle. And what is this principle? This principle is 1 plus 1 equal to 2. It sounds like, yeah, ridiculous, but that's what it is. When I say is 1 plus 1 equal to 2, it means the waves that we are talking up to this point, they are all linear waves. When you say linear waves, means, look at this figure right here. If we have two waves approaching each other, one has the displacement y1, the other one has displacement y2, or you can think of it like an amplitude of that source. And if these two waves meet at one point, the net result is going to be simply the addition of the two. Nice. And if you let it go, it's just gonna pass each other by, and that's it. Just like nothing happens. That's a property of waves. Okay. So the reason I say why is so simple, because lucky for you, lucky for me, lucky for all of us, that when two waves meet, you don't have to go like Pythagorean theorem, or you don't have to do like cubic summation, or square root or something, or it's just summation. So nature has some mercy. So that's nice. Okay, so that make it nice in the sense that then you can get to the two extremes of the interference. So that means the first extreme, of course, you already saw this one, the displacement is in the same directions. So the net result of the superposition of the two waves, you're going to get a constructive interference. So it means the final result is taller. Okay, the transverse displacement is actually added. On the other hand, you might have the opposite effect when you have the displacement that actually point in the different direction. I mean, in this case, opposite direction. Then you get some cancellation. So if the cancellation is sort of perfect, then you get completely nothing out of it. That's also possible. But no matter what, when the displacement's pointing in the opposite direction, you get a destructive interference. Okay? And where have you seen this in your digital world at this point? I don't know, many of you use it or not, but when you do the noise canceling headphones, that's what this is. So that's why noise canceling headphone needs some battery, because actually you have a microphone built into your headphones. And that microphone has to listen to the ambient sounds. And once the microphone receives the ambient sounds, it flips that sound wave half a cycle, 180 degree, or you can think in terms of the pi angle. Then you generate an opposite displacement to an incoming wave of the new ambient sounds. So by combining the two, then you are pretty much get rid of the ambient noise. Okay, that's the idea. Okay, so that's what it is. So that will be a microphone along with the circuits that flip the phase or flip the shape of the wave 180 degree, and then try to combine that to a new incoming waves and hopefully just get rid of stuff. Okay, so that's kind of works so well with the ambient noise, because we assume that the ambient noise doesn't sort of fluctuate so much. So it seems to be easy to cancel. But when you have like a, you clap your hand, when you clap your hand, then there'll be a spike in the sound, then you might not have enough time to flip the phase and cancel out and everything. So there might still be some leaking for the noise when you have like a big powers of sound coming in, all right? But because the circuits nowadays so fast, they can calculate everything so quickly and everything, so the noise canceling ability is so high now. It's super quiet. Yeah, so that's kind of good. But I haven't used much anymore. To me, it's too quiet. Somehow, we still want to hear something going on around us. Yeah. So, okay, that's kind of dangerous too, right? Yeah. When you walk on the street and you don't hear what's going on around you at all. Yeah. Okay. All right. Cool. Okay. The concept of this one, actually, we can go back all the way to the sinusoidal waves if you want. The reason I say you can go back to that all the way, because the basic concept is very simple. It's just displacement summation. So that means you can express your waves in whatever you like. It doesn't have to be sinusoidal waves. Y1 could be whatever function. Y2 can be whatever function. Once these two waves meet, just sum them up. That's it. That's how simple it is. But of course, we're going to focus on the sinusoidal waves because that's the easiest wave, and it is something that can showcase a good property of this. All right. Just a second. There is a toy in here that's, I think, is voice activated. I just clap my hand and it just wake up. Okay, here we go. So what you have over here is sinusoidal waves. However, we already learned a little bit about that phase constant, yeah, toward the end. By having that parameters toward the back, that's when you adjust your phase, because we already learned that by having that extra phi, that number there, it's just you're just sliding your wave a little bit, whatever you like. And one thing that I can talk right away, and then you would probably agree with me right away now as well, is if I shift it by 2 pi, what will happen? I don't know how to turn this thing off. Oh, there is an off button here. Okay, wait a second. It's kind of cute. Okay, here we go. So if I slide the wave by 2 pi, what will happen? Burn it. What is that? Okay, when you what burn what burn, well, no, don't burn the toy. Okay, 2 pi means you slide the wave by complete one cycle of waves. If you think in terms of the position, it means you slide it one wavelength, or if you consider in terms of time, so it means you waited for one period. So everything will just come back to the original shape. So that's good. So if this is perfectly 2 pi, you get back your sinusoidal wave. You see what I'm saying here? And then you can do it 2 rotation if you like. I can go 4 pi if I want. Everything will come back to the original shape again. You're not going to be able to distinguish between the shifted, slided wave or not. It looked the same with the other one. Or you can keep going 6 pi on and on. So as long as you shift the wave by the full or multiple of complete cycle, the wave will come back and look exactly the same. Cool. On the other hand, I can do the other way. If this difference is pi, what will happen, you think? That is your noise canceling headphone. When you shift the wave by half the cycle, that is when you get the displacement to go opposite direction all the time. Yeah, because you slide it half of the cycle. And of course, you can do it 3 pi. Because you do it pi, and then you go around one more cycle, everything will come back to exactly what you saw before when you were at pi. So you can do 5 pi on and on. You can do odd multiple of pi. That will do the job. But in this case, you get cancellation effect instead. So what I'm trying to say here is when the phase difference is even multiple of pi, you get constructive interference. And we say these two waves are in phase. In phase. I don't know what on the side, in phase, up and down in the same direction. Okay. On the other hand, when the two waves are going opposite, I don't know, is this a good representation or not, but one up, the other one is down, you go up and down like this, that is the out of phase case. And at the end, you get a complete destructive interference. Okay, so if this wave is a sound wave, so that means the constructive interference, you will hear the sound twice, I mean, not twice as loud, but I mean the amplitude of the interference will give you at twice the size of the original amplitude. And when you have the out of phase case, when they are destructively interfere, then everything will turn quiet because it's completely subtract themselves back to 0. Okay, sounds good? All right, so if you get this idea, then of course, some other cases that's not odd multiple of pi or even multiple of pi, you will get somewhere in between. And for that, you need to really do the summation of the two waves. All right, but of course for us, we don't need to do that because it's more like a numerical calculations. You just add two waves together and then you can use trigonometric identity to do like sine A plus sine B equal to 2 sine of the sum over 2, cosine of the difference over 2. I mean, this is something that you can refer to the formula table all the time. And then you can just crank up this number and then get what should be the final waves combinations. Yeah. All right. But the two extremes that we're going to focus on is the constructive case and the destructive case. And somewhere in intermediate in between, just take care with mathematics. And of course, in the exam, we are not trying to do that because it's just plugging in. So it's kind of like not a good test of sort of physics understanding or anything. Okay, so we're gonna focus on two extremes. Okay, in phase and out of phase. Constructively interfere, destructively interfere. Okay, and here we go. So when you turn that into a realistic approach, of course, well in realistic life, who would want to measure the phase, right? When you have like a speaker away from you, you're not gonna like ask like Ajahn, you are at like 16 pi angle away. No, of course, nobody says that. You're going to talk about the distance. That will be the easiest way to talk about. So that's what it is. So usually when you measure the distance. So think of it this way. If you have a source and you somehow split the source into two ways, two paths, okay? So that means it could be a real two sources. That's possible. Maybe I have some figure later. Here we go. For example, you might have two speakers. Okay, so there are two sources, like source number one and source number two. All right, so the waves that coming from two sources will travel with their own distance. So you can call that distance R1 and R2. So you can think of R1 to be the distance from the source number one towards the observer. R sub 2 will be the distance from the source number 2 toward the observer. Okay. And now how can we get from that distance to this phase? The answer is very simple, because we know the relationship that every time you talk about the phase, the 2 pi always mean one wavelength. You guys with me? That's all the time. So that means every time that you talk about the distance of one wavelength, one lambda, that means 2 pi in phase. I'm gonna say in cycle. 2 pi in phase or in angle. Yeah. So now you get a conversion factor between the actual length in meter and phase in radian. Okay, we're not gonna use degree here, just use radian. Okay, sounds good? So what I'm saying is, all we care about is the difference, because what we are trying to look at here is, here, the phi is the phase difference. Yeah, the phi representing the phase difference. So the key point is, you want to turn the phase difference into length, you just use this conversion factor. So here we go. So what I'm doing is, I just want to turn the path difference. You guys with me? Okay, one more time. R1 is the distance from source number one towards the observer. R2 is the distance from source number two toward the observer. You just take the difference. And then you just looking at that difference. That, hey, when you have that difference in meter, I just want to convert that meter into radian. Yeah, into phase. And all you need to do is just check if the phase hits the even multiple of pi. If it hits this, it's going to be the constructive interference. If it hits the odd multiple of pi, you're going to get the destructive interference. That's it. See, it's kind of like, okay, let's hear. If I call that path difference the delta R, okay, that's a path difference, yeah, delta R. And because I have this conversion factor waiting for me, so I can convert the delta R into the phase by simply multiply by the 2 pi over lambda. You guys with me? Because the phase changes by 2 pi every lambda. So that means if I move by a distance of whatever, which is whatever now we call delta r, all I need to do is just multiply that delta r with the 2 pi over lambda. Then I will get that phase difference that we are talking about. Let me give you a simple example. If the delta r equal to perfectly, oh no, that's not a good starting point. If it's 0, no path difference. If there's no path difference, the phase difference will be 0. And which case would that be? That would be the first case. Okay, I forgot to put the 0 in here, of course, but that's the easiest possible case is when there's no phase difference at all. So the two waves appear to the observer to be exactly the same. When I use it, I don't know, is this a good representation or not? But to the observer, which is me at this point, these two waves look exactly the same. So when the two waves look exactly the same, it will just add up. You get twice as big. That's a constructive interference. Try again. If the delta R is one wavelength, perfect. So that is exactly one full cycle. So what you're gonna get for the phi? You plug in the lambda into here, lambda cancel, you get 2 pi. And that makes sense because when the distance are separated by one perfect wavelength, the phase are separated by perfect one cycle, and that is 2 pi difference in phase. But from the point of view of the observer, the two waves will look exactly the same again. You guys with me, yeah? Yeah, it looks like I'm crazy here on the screen, but that's what it is. So good. Let's keep going. What happened if the path difference is 2 lambda? You can guess now. The phase difference will be 4 pi, and that would be constructive interference again. So now you can get the conclusion here. If the path difference is a multiple of wavelength, that's when you get a constructive interference. Nice. Try again. What if the path difference is half the cycle? When you say half the cycle, in meter is half the wavelength. And when you plug into this, half the wavelength, you will get the phase difference to be what? Pi. And when you say it's pi, come back here, Adan is right here. And that is going to be the out of phase look, and that will be the destructive interference. Cool. Try again. If, I mean, what other choices do I have? Of course, Adan turn one more round. Okay. So I get half of the cycle with an extra round. So I translate for extra wavelength, nothing changed. So I'm going to get 3 lambda over 2. So what will be the phi in this case? Of course, 3 pi. And everyone sees the pattern now. I can move on to 5 lambda over 2. The phase difference I'm getting is going to be 5 pi. On and on. So that means if my path difference, here, look at this one, is 1, 3, 5. So if you have path difference of the odd multiple of lambda over 2, you get destructive interference. But in terms of the logic, you might not even have to memorize these formulas at all because it's just a pure straightforward conversion between the distance into phase. Let me use this. Distance into phase. Every one wavelength equivalent to the phase rotation of 2 pi. If you want half the wavelength, rotation will be just half the pi. And then you can always add extra cycle to any cases that you want. Is that reasonable? I hope. All right, so if you get this one, Okay, the application of this is not limited to the sound. It's just easier for the the everyday experiences to talk about sound, because when I say, hey, if it's destructively interfere, it means you hear nothing. So that's okay. Everyone can relate to everything will be quiet. And if you say like constructive interference, everything will be louder. Okay, you can sort of a little bit imagine. But another example that also works is with the visible light. But visible light maybe is not common for everyday's life, because the light, the visible light that you see around you is multiple frequency. So that's why you don't see the interference effect in your household lighting. No, you're not going to see it. You usually will see it in the physics lab or something like that. That when you have the source that give light at only single frequency. But for the sound, to have single frequency seems to be quite easy, because you can just download the app and then just like, hey, give me whatever 500 hertz sound, and then you can generate single frequency sound. But if you turn this thing on and then, hey, give me 500 nanometer light, usually you're not going to get like single frequency lights. So that's kind of harder for you to see interference effects in light around you. Okay, but it works. I mean, this concept of interference of waves works with any kinds of waves. It doesn't have to be just only sound wave. Yeah, light wave works, water's wave works, strings wave on a string works everywhere. Okay, very good. All right, let's take a look at some examples. All right, so if we get this thing done, then I think that's it. That will cover everything for your midterm, and we should be in good shape. All right, so two traveling sinusoidal waves are described by the wave functions below, assume as I units already. What is the amplitude and what is the frequency of the resultant wave? Okay, this is the case that I'm going to show you that the underlying principle of the superposition of waves is simple summation. Seriously. All right, that's the point of this example right here. That's it. Your resultant wave is this, y1 plus y2. And I was serious about when I say just adding the two, just add them like this. Wow, that's nice. There you go. And that's, oh, I think I saw a typo here. It's a T, not supposed to be tau. Okay, just T. Okay. And you just add them. Okay. And you got the formula over here. Okay. Psi A plus psi B. You just do them straightforwardly like that. So it's going to be 2 times 5. Okay. And then you can do psi or cosine first, up to you. But if you want to follow that formula, will be the cosine of the difference over 2. So when I take the difference of the arguments, then I get 0.25 pi, and then I divide it by 2. That's the one for the cosine. And I do the same thing for the sine, but now the arguments in here is going to be the sum of the 2 divided by 2. So I just add these two brackets together, divided by 2. I still get 4 pi x minus 12 pi t. And here we go, 0.25 pi over 2. Okay, all right. Let me sort of like rearrange this to make it a little bit cleaner. So let me put pi over 8 there. And it's still sine 4 pi x minus 12 pi t minus pi over 8. Here we go. And that's it. It's done. Seriously.
How did 2 times 5 come from? Where did it come from?
Which one? 2 times 5.
2
Oh,
times
okay.
5 ครับ
It's come from here, guys. Yeah, number 2 right there. So this identity You have the factor of 2 in the front.
I see ครับ
Okay, no? And then so when you come here, because I have a common factor of 5, so I pull 5 out to the front and then multiply by that 2 from the identity. Okay. So what is the amplitude? So, okay, after completed this summation, everything goes back to the questions of reading the sinusoidal wave function. You guys still remember from the previous lecture. So if you are given this last line here, and I'm asking, hey guys, what is the amplitude of this sinusoidal wave? Whatever that comes out in the front, that's your A. Okay, just use this as a review. That's kind of nice. You have to take the cosine pi over 8 along with it too. Okay, all right, because 10 now being multiplied by that cosine pi over 8. And whatever come in the front of sine and cosine, we will take those to be amplitude. Cool. And what is the frequency, guys? Yes, yes. Can you look at it? Yeah. Oh, done. Whatever numbers in front of t, that is your omega. And omega is 2 pi f. So that means 2 pi f is 12 pi. So f is going to be 6 hertz. See, so that's the good things that now you guys know how to read the sinusoidal waves now. I can even add on top of this, the numbers in front of x is your k. K is 2 pi over lambda. So I can say that the lambda is 0.5 meter if you want. Cool. And from here, you know the frequency, you know the wavelength, you can figure out the speed of this wave. So this reminds you what happened with the sinusoidal waves characteristics. However, we have extra of this, no problem. That's just slide the wave by a bit. And that's your resultant wave function. Okay, you guys knows how to do this now, yeah? This one is already definitely will be in the exam. So that's why I kind of like, remind you this. Hey, don't forget to, study how to read the sinusoidal wave functions. You should be able to extract the information from these sinusoidal waves. Cool. All right, try again. Next one. Okay. Actually, this one you can skip, I think, because I try a couple times. It seems to be more confusing because for our lecture, we always focusing on the interference between waves that having the same frequency. But this one is sort of is the waves that having the different frequency, different wavelength and combined. So this will give you some, it would throw you a bit off course. So I don't think this is a good exercise for us at this point. So that's okay. You can just, this one, you can skip this one. That's all right. Doesn't hurt anything. Okay. All right. This is the things that I think is more realistic in terms of the actual application, because it is something that you can measure and then try to calculate. Okay, try this one. I think this is going to be a good one. A pair of, good one for the midterm. A pair of speakers placed 3 meters apart and are driven by the same oscillator. So that means these two speakers give out the same sound waves. A listener is originally at point O, which is located 8 meters from the center of the line connecting the two speakers. So that means point O is right in the middle. Perfect. The listener then walks to point P. So listener walk up a bit, which is a perpendicular distance by the distance of 0.35 meter from point O. Before reaching the first minimum, so that is the clue, guys. Reaching the first minimum in sound intensity. So that means that is the first position that you get the destructive interference first, because it could be multiple, right? What is the frequency of the oscillator? All right, let's try this one together, guys. But this should be straightforward though, because all you need to do is you get the clue already. This is the first minimum. So if I'm asking you in terms of the phase, the first minimum should give you what is the phase difference. Oh, I'll answer that question a little bit later. How many questions? Okay. So for the first minimum, what should be the phase difference? What do you think? So think about it. When you are standing at point O, you're not going to have any phase difference. So this means at point O, the phase difference will be 0, correct? And then, of course, when you walk away from point O, then the wave will start to sort of like, you know, out of sync a bit. But then once you reach point P, the problem says that will be the position of hearing the first minimum. So what should be the phase difference at P, you think? Very good. It's supposed to be pi. Guys with me? Because if you go back to this one, that will be the sort of like the smallest phase difference that you start seeing something. There are only two things that you want to see, either the perfect cancellation or the perfect additions of the two. But the first one you're going to hit first is when the phi equal to pi. So it means you're going to hit the minimum first. However, now you understand the logic here. If you keep moving up, so that means there might be another point up here. So let me add another point here. Yeah, so when you move up at green point, maybe point Q, that would be the point where the phase is now, it's going to be 2 pi. So it means you're going to hear the loud sound again. And if the question talking about that point, they might mention of that point for having the first, well, I would say the second, or maybe the first maximum from point O. Because point O is supposed to be maximum, of course. So point Q will be the first maximum away from point O. Okay, you see what is about to happen? If you keep walking up, then you will hear the quiet sound one more time. And that is when the phase difference will be what? 3 pi. And you keep walking up again, you will hear the loud sound again. And that's when the phase difference is 4 pi. So you go, just keep walking up, you're gonna see 1 pi, quiet, 2 pi, that's loud, 3 pi, quiet, 4 pi, that's loud again, 5 pi, that's quiet, 6 pi, that's loud again, on and on. So you see it and alternating between quiet and loud, quiet and loud. So if I'm speaking in terms of the light, so you're gonna hear the dark and the bright, the dark and the bright, the dark and the bright. Same thing, same idea. Okay, sounds good. So for us, speaking in terms of the phase, we know the first minimum mean the phase difference is gonna be pi. Okay. Speaking in terms of the wavelength, the path difference must be what? 1 pi, guys. That's half the cycle, and that will be half the wavelength as well. And that's it. What I'm getting is gonna be R2 minus R1 difference. I don't care. I just need the path difference. So that's why I put an absolute sign here. But from the figure, we know R2 is bigger than R1. So you're gonna get positive sign out of that. Equate that to lambda over 2. Done. So that's a nice thing about this interference. It's more like, it's like a counting problems. You just count by knowing the conditions of what will give you the cancellation, what kind of condition will give you the summation, I mean the perfect addition of the waves. Okay, so if you want to memorize in terms of the formula, that will be fine. It will meet this case right away. So it means the path difference R2 minus R1 is going to be the destructive interference for the first time. When you say the first time, when you look at this formula right here, the first that you're going to be able to meet is when n equal to 0. That's the first. That's the first minimum. So you can substitute 0 into this expression and say delta R is going to be lambda over 2. Same as what we just got over here. Okay, guys? Sounds reasonable. And actually, if you looking at this one from some textbook, they might just put it like -1 instead. That will work too. So if they put the formula for the odd numbers to be 2n minus 1, so n starts at 1, on and on. But if some textbook put 2n plus 1, then n start from 0. Okay. And actually, come to think of this one, I prefer the upper one better. I prefer the 2n minus 1. I don't remember why I put 2n plus 1 there. Maybe survey textbook use a plus. I don't know. The reason I prefer the 2n minus 1 because n start at 1. And when n equal to 1, it means the first minimum. So that sounds sort of in sync with the first, second minimum when you really observe the sound. Okay, all right. So I hope you see I can arrive to this conditions or this expression by just doing just a pure sort of reasoning of what should be the phase difference first. And once I know what is the phase difference, I can turn it into the wavelength. And once I have that wavelength conditions, and that's it. So the lambda is just twice of the R2 minus R1. And then the frequency will be just V over lambda. And V usually given to be like maybe 340, 345. You can plug it in there. And then you divide it by 2. Now, the complexity of this one is just calculating the R2 and R1 through Pythagorean theorem. It's number crunching a bit. So R2 is just square root. From the look of this one, it's this triangle right here. So it's going to be 1.85 square plus 8 square under square root. And R1 will be the upper triangle. So that will be square root 1.15 square plus 8 square under square root. Okay, but once you punch the calculator, then you should be able to get that number here. R2 minus R1, and you're done. Okay, sounds cool. So in terms of, I think, interference of waves, the logic is here. That's it. You can either speak in terms of the phase difference or you speak in terms of the path difference. But path difference seems to be sort of more practical because that's what you can actually measure easily. So that's why we just have to have a conversion factor. And the conversion factor is simple. Every 2 pi change in phase equal to wave traveling by 1 wavelength. Nice. Okay, that about the question, how many questions in the midterm? If I remember correctly, 12. 12 questions in the midterm. Yeah, and then actually I can announce this in line group as well. So the rest of us can serve. Okay. Yep, definitely. Okay, cool. Okay, let me type it right now before I forget. Midterm has 12 problems. Here we go. It's in the light group. Okay. All right, guys. I think that's pretty much complete the whole business of things. That is the last portion of this bit. But to be honest, I think I'm gonna just park it here. The reason is because I don't see it in the midterm. And I'm not sure why. Good like that. And I'm not sure. Ajahn Thane told me to teach this one, but I didn't see this in the midterm. So I'm not sure. He might not have enough time to get to this topic or not. I'm not sure. But I don't want to add anything to the material anymore. So we still have Saturday. If anything happened to this topic, then I can still have some time to let you know. Okay, but at least up to this point, I think we are in good shape for the midterm. Okay, so I think uh, it's safe to say that don't worry about this topic, even though it's the same idea, but there is some complications that you have to actually learn how to deal with this. And it will be a disaster if you learn how to do this, but it doesn't show up in the exam. You guys will be pissed. Okay, to save your time and save everybody's time. So let's, okay, forget about this one for now. Okay. And so this is a good exercise, good examples for the midterm. And I can say right away, the midterm we're gonna look like this because there's nothing else to ask. Okay. All right. Don't forget to check out the extra problems that I put in the handouts folder. Okay. And then I will put the class notes in the drive as well. Yeah, I forgot about that one. Okay. So I'll upload the class notes PDF into that note folder. Okay. All right. So if this is good, any questions, guys? Okay. If not, I think we can call this done, and that's complete the material that's going to be covered in midterm. I think that's everything.